We're continuing our discussion of the LIGO experiment problem. In part A, we calculated the amplitude of the electric field. Now in part B, LIGO can detect a gravitational wave that temporarily lengthens one arm by the minuscule amount of epsilon equals 10 to minus 18 meters. When this happens, the beams combine with a phase difference of pi plus delta. Estimate the shift delta in radians. Note that the phase difference accumulates during both traversals of each round trip. Alright, so let's remember how the Michelson interferometer works here. We have a monochromatic light source in the Michelson interferometer, and this is going through a beam splitter, so you can see that it goes through the beam splitter once, it reflects and goes through it again and goes to mirror 2, and then retro reflects from mirror 2 and goes through the beam splitter again and reaches this point. And also the part that goes through the beam splitter once, now part of the intensity is transmitted. It goes through the compensator plate, which has the same thickness as the beam splitter, retro reflects from mirror 1, and then goes through the beam splitter at the compensator plate again and reaches this point. Now, if you follow this, you can see that the waves coming from the source go through the beam splitter once, twice, and on the way back 3 times. And for the one that is reflected from M1, it goes through once, the compensator plate once, and the second time from the compensator plate, the same thickness as the beam splitter. So the path difference that occurs in the beam splitter is compensated for. So the only path difference occurs between the traverses from mirror M1 and M2. So it's going to occur during the travel in distances L2 and L1. Okay. Now with that we can see that ray 1, which is the one that was splitted in the beam splitter and going through M1, is going to make 280 round trips before reaching the point P that we are observing. And ray 2 will go through the length L2 2 times before it reaches the point P. And as I said, the path differences occurring in the beam splitter are compensated for. Okay, so ray 1 makes 280 round trips, ray 2 makes 280 round trips. Now, what is the relationship between path difference and phase difference? The phase difference that will occur, delta, divided by 2 pi, is equal to the path difference divided by the wavelength lambda. So in one wavelength, we develop a phase difference of 2 pi. So we can see that the relationship between phase difference and path difference is delta is equal to 2 pi over lambda, 2 pi over lambda times the path difference, delta L. Now, what was the original path difference between these two rays? Ray 1 travels this distance L1 twice, and ray 2 travels this distance twice. So the original path difference between them before they hit point P is 2L2 minus 2L1. What's the final path difference? What do I mean by the final path difference? This movable mirror M2 is displaced by an amount epsilon. So the distance that ray 2 travels becomes, instead of L2, L2 plus epsilon for one way of the travel. So it's going to be, path difference is going to be twice L2 plus epsilon minus 2L1. That's the distance traveled by ray 1. So this is going to be equal to 2L2 minus 2L1 plus 2 epsilon for a one round trip. Okay, So if I compare these two situations, the path difference delta L between the two situations, delta L final minus delta L initial, is equal to 2 epsilon for each round trip. Okay, so the total path difference, delta capital L, is going to be 2 n epsilon for n round trips. And we have 280 round trips here. So the path difference that will develop, the phase difference that will develop is 2 pi divided by the wavelength lambda times the path difference 2n epsilon. So we will see that for 280 round trips, the phase difference that will develop is equal to 4n pi epsilon divided by the wavelength. Now we can quantify this. The phase difference that we are trying to measure is 4 times 280 round trips pi. We moved the mirror by a minuscule amount, 10 to minus 18 meters. The wavelength was 1064 nanometers, 10 to minus 9 meters. So the phase difference that we're trying to detect is 3.3 times 10 to minus 9 radians for this overall process. Okay, so let's summarize what we did here. So remember that we're using a neodymium YAG laser with lambda 1064 nanometers. The beams traverse both arms both ways 280 times before recombining at this point P, where we're looking at. And the devices are tuned so that the beams destructively interfere when they recombine if no gravitational wave is present. In part A, we calculated the amplitude of the electric field corresponding to this beam power, 100 kilowatts concentrated into 1 centimeter square area. In part B, we're looking at the phase difference that will accumulate during both traversals of each round trip if we move the temporarily one of the mirrors by a minuscule amount, epsilon equals 10 to minus 18 mirrors, so that the beams will combine with a phase difference of pi plus delta. So this is the phase shift we're looking at. So remember, they were tuned so that they would destructively interfere, so that the phase difference would be pi. Now it's going to be pi plus delta. Now, I looked at the distance traveled by ray 1. It is 2L1 for a round trip. And distance traveled by ray 2, it's 2L2 for a round trip. And the phase difference that develops divided by 2 pi is path difference divided by lambda. So the phase difference is 2 pi over wavelength times delta L. The initial path difference was 2L2 minus 2L1, corresponding to a phase difference of pi. The final path difference is 2L2 plus epsilon, because this mirror has been moved by an amount epsilon. So we have 2L2 plus epsilon, L2 plus epsilon, 2L2 plus epsilon. So between these two situations, we have a path difference of 2 epsilon for each round trip. And for n round trips, we have 2n epsilon path difference, corresponding to an additional phase difference of 2 pi over lambda times 2n epsilon for n pi epsilon over lambda. So instead of having a destructive interference, we're going to now have a phase difference other than pi, it's going to be pi plus delta, where delta is 3.3 10 to minus 9 radians. So we're trying to detect the presence of gravitational waves. If the gravitational wave temporarily lengthens one arm by a minuscule amount, 10 to minus 18 meters. So that's basically what we are looking for in this situation. So we have found the total phase difference introduced by the presence of a gravitational wave if it results in a temporary motion of the movable mirror by an amount epsilon.